Okay, this video is dedicated to exponents and the fundamental properties that go with it. So let's first do this warm up to understand what exponents are. So let's go ahead and take a look. Here we have a great example where we have 7 plus 7 is 14. So that is repeated addition. Or we could say that's 7 times 2. Okay, so multiplication is repeated addition. Okay, whereas 7 times 7 is 49. And exponents, that's what it is, repeated multiplication. So 7 squared means 7 repeated 2 times through multiplication. So that's 49. So let's make a little note down here. Multiplication is repeated addition. Okay. Whereas exponents is repeated multiplication. Okay, so that is the key difference here between the two. So let's look at some more here so we can see the comparison. So first I'm going to do addition. 3 plus 3 plus 3. So that's repeated addition. So that's going to be 9. And that's the same thing as 3 times 3 is 9. So we can see that those two go together. Okay. Whereas 3 times 3 times 3 is 27. Okay. And here we could say, okay, how's it look as an exponent? 3 cubed means 3 repeated 3 times through multiplication. So that also is 27. So those two things are the exact same. So look over here. 9 plus 9 plus 9 plus 9 plus 9. That's really 9 times 5, which is 45. Okay. Now let's jump down here. 9 times 9, 5 times. That is the same thing as 9 to the 5th power. Now again, to get that, let's see what that value is. So we're going to turn on a calculator and do 9 raised to the 5th power is equal to 59,049. Okay, so 59,000. And notice how big it gets, okay? And that's the same value as 9 to the 5th power, okay? Now here we can see 9 cubed times 9 squared. So that means 9 repeated 3 times 9 repeated 2 times. So if you look at it, there's 9 cubed, and then there's 9 squared, okay? So that's the same thing there. So this answer down here is also 59,049, okay? One last example down here. 4 repeated 4 times through addition, so that's 16. And here we have 4 squared, which is 16 times 4 squared. So that is really, there's 2 4s here, 2 4s here, for a total of 4 4s. So what's 4 to the 4th power? Let's go ahead and take a look here. So we're going to go 4 raised to the 4th power is 256. Okay. So this is 256. And this is also 256 because this both means 4 repeated 4 times through addition. Now this is the same thing here. This is 4 square repeated twice. And where do we see that? Right here. 4 square repeated twice. So this 2 is 4 to the 4th power, which is 256. So what we're looking at here in this video is how do we represent exponents in different formats, and they really all mean the same thing. What happens when we multiply the bases? What happens when we have parentheses? What happens when it's all combined to one thing? Okay, so the key thing to remember is exponent is repeated multiplication. So let's take a look at the pieces of exponents. So we call the 4, the big number, the base. Okay, and the bases never change. And that's key in these examples. Whereas the 2, we call that piece the exponent. And that tells you how many times being multiplied. Okay, so the number of times being multiplied or repeated. Now the entire thing is called the power. Okay, so here we'd say the power is equivalent to 16. 4 times 4 repeated twice. So that really means 4 times 4 is equal to 16. So we'd say the power is 16, the entire value of this expression. Okay, so base, exponent, and power. Now here are basically different formats of how we're going to see exponents. Let's just talk about what we have here. x to the n power. Now again, these are all variables, so x and y will be base numbers. And notice the m and n's are exponents. So here we say, okay, if we have x repeated m times and x repeated n times, really x is repeated how many times? M plus n. So here we add the exponents. Okay. So here, this means that x to the m power is repeated n times. So we multiply m times n. Okay, and we just show the base once. Okay. So here we have x and y together repeated m times. So really what we want to do is show x to the first power, y to the first power. So that means it's repeated once. So those are like imaginary ones. We don't have to show those all the time. But when it's m to the outside, we want to distribute exponent to exponent. So really this is going to be x to the m power, y to the m power. Okay. Now anything repeated to the 0 power, so that means how many x's are there? There's 0. So we have the imaginary 1 in front, so this actually equals 1. The absence of anything in multiplication is equivalent to 1. Now x to the negative n, that means it's in the numerator. When you see a negative exponent, you want to flip it and make it positive and put it in the denominator. So this is a very big concept. Okay. Now, when we do division, notice the n is in the denominator, so therefore it's negative. So what we want to do here is to take this n, we want to move it upstairs and make it negative. So this is x to the m power times x to the negative n, which is really x to the m minus n. Because notice here, with the bases that are the same, we add exponents. Well, if we add a negative, it's the same thing as subtracting. So that's a lot like this example up here. Okay. Now here, this like we did with the parentheses here, if it's a division problem, no problem. Put your imaginary ones in and then distribute n to every exponent. So that's x to the n power divided by y to the n power. Okay. So this just shows you fundamentally what we have here. Okay. So let me go ahead and erase this. And then we'll go through examples using numbers so you can see a better example of what we're talking about. So this would be like x squared times x cubed. That equals x to the fifth power. You add the exponents. Here we have x squared raised to the third power. There we multiply exponents and we would get 6. Here we would have like 2 times x raised to the third power. Okay, so what we do is put our imaginary ones in, distribute, and we really get x cubed times, or I'm sorry, 2 cubed times x cubed. And obviously 2 cubed is 2 times 2 times 2, which is 8x cubed. So notice how we keep the bases the same. Notice I did not change the 2x. The only thing I ever changed is the exponents. This is like even 2 to 0 power. How many 2's are there? There's none of them, so we have 1 and it's absent. So this is like 2 to the negative first power. We'll change it into a fraction and then flip it, put the 1 on top, put the 2 on the bottom, and make it a positive 1. So that's the same thing as 1/2. Here we have x squared, x doesn't make cubed, divided by x squared. Well, we're going to change that to x cubed, move this upstairs and make it negative, and then basically subtract them. So we have 3 minus 2, which is x to the first power. Okay, so that's the equivalent of this example here. And then over here, just got carried away here a little bit. So don't worry about this one. So this is like x over y to the third power. So put your imaginary ones in and distribute. So that's x cubed over y cubed. Okay. All right, so let's go ahead and look at some more examples. The best way for this topic is just to do multiple and multiple examples to see all different formats. So here I see a common base, so I want to add the exponents and get 11. Here I have a common base, so I want to add the exponents. So what's negative 4 plus 6? 2. Here I'm going to rewrite it, put my imaginary ones in, put exponent on everything, and then distribute. So that's 2 cubed x cubed, which is 2 to the 8th, whoops, sorry, 8x cubed. So we did this one just on the previous page, same example. Here, I'm going to subtract it. Now again, I'm going to take that 2 to the 3rd power, move it upstairs, and make it -3. Or I get to say 2, 5, then -3, which is going to be 2 squared, which is going to be 4. Okay. Now here, this is 2 to the 1st power, x to the 0 power. The 0 does not belong to the 2. So this is really 2 to the 1st times x to the 0. The exponent only belongs to the base directly associated with it. Otherwise, we'd see parentheses like this. So this is 2 times 1, because that goes to 1, which is this 2. Okay. Here, put your imaginary 1s in. Now this has an exponent, so I don't have to put anything there. And distribute the 3. So that's 2 to the 3rd power on top, and then 2 squared to the 3rd power. So here I'm going to multiply exponents and get 6. So that's 8 over x to the 6th power. Okay. So there's some great examples showing a little bit more variation of what we're looking at. Now here's a good little exercise to show you how negative exponents work. So let's start with what we know about 2 to the 0 power is this 1. 2 to the 1st power, that means there's only one 2. 2. 2 squared means 2 repeated twice, which is 4. 2 cubed means 2 repeated 3 times, which is 8. Okay. Now, if it's to the negative first, that means division. So it's 1 over 1, 2, which is 1/2. This just means 1 over 1 divided by, because it's a negative number, so it goes in the bottom. So 2 repeated twice, which is 1/4. 1 over 1, 1 over 4. And the same thing over here. 1 over 2 repeated 3 times, which is 1 over 8. So notice we have the same numbers put in different positions. So the negative means you put it in the opposite position. So when I see 3 to the -5, that's really 1 over 3 to the +5. Put it in the opposite position. Switch it from numerator to denominator. Same thing here, 1 over 8 to the 1st power. Now, if it's a negative in the bottom, to make it positive, we just put it in the opposite position. So it's not always the denominator, you just have to change the position. So it's really 4 to the 5th power over 1. Okay? And again, you could put this in your calculator and figure out what that is. Now here's the thing, this is 2 to the 1st power. That's positive, so I keep that in the same position. This is the only thing that's negative, so I only move what's wrong. So that's x to the 71st. So that's what that one wants to look like. You only move what has a negative exponent. If it has a positive exponent, like we see right here, you leave it alone. Now the last thing we want to show here is let's combine all these steps in multiple problems put together. So here's kind of the little steps I like to do. First we want to do is make all the exponents positive. Okay, we don't like to work in negative exponents. Next thing we like to do is get rid of the parentheses. That's where we distribute exponents. Now honestly, these two steps can interchange. Okay, so sometimes you might do the parentheses first and then make it positive. After that, you want to combine anything that has a common base. X's with X's, A's with A's, numbers with numbers, and so forth. And always at the end, you want to reduce and simplify. Okay, so let's take a look here. Now this negative has nothing to do with exponents. So that's really like a -1 times 5 to the 1st power times y to the -6 power. So that's how I see it. I see it as like 3 separate pieces. So when I put that together, the -5 stays on top, but this has to become positive and you move it to the bottom. Okay, so that's first step, make all positive exponents. So that's my final answer for that. Now here what we want to do is first make everything positive. So the 3, that's to the positive 1st power. Put exponents on everything. So 3 to the 1st, no problem. C to the 6th, no problem. Now D to the -3, I want to move that downstairs. So I'm going to put that down here. D to the +3. Now let's do the bottom. 3 to the 1st, fine. I'm sorry, that's 36 to the 1st power. Should go there, not there, sorry. C to -4, make that positive, so put it upstairs. And in D to the 8th, that's already positive, so leave it alone on the bottom. So now I'm going to go ahead and associate. I'm going to see, okay, numbers with numbers, 3 and 36. Okay, so those go together. So what's 3 divided by 36? Reduce that to 1 over 12. Just numbers. Don't worry about the exponents. Now let's look at the C's. We have two C's together on the top, so that means we add the exponents. That's C to the 10th power. Then the last thing we look at is the d's. They have a common base. They're both on the bottom, so we add the exponents on the bottom, and we have d to the 11th power. And there is our answer to that problem. Okay, let's see, look a little better. Okay. Now again, you don't have to show this one because we already have something on the top, so if you want to ignore that, you could. So that's what it looks like. Notice all the exponents are positive. Now this last one here, the only thing that we have to move is the negative exponent. Now the j cubed, that is fine where it's at, so leave it alone. So the h has to move upstairs and become positive. Now notice you could put it over 1 if you wanted to, but that's understood to be a whole number, so we just leave it like that. Okay, the last example here, I'm just going to rewrite it down here. I'm going to move what is negative. So that's negative, so it goes in the bottom. That's negative, so it goes in the bottom. That's positive, so it stays on the bottom. Okay, so that's a different a cubed, and that's positive, so keep it on the bottom. So notice there's nothing left on top, so we put a 1. Just going to rewrite over here so we got a little more room. So we have repeated a, so we add the exponents, that's a to the 6th power. And then we have repeated b, so that's b to the 8th power, so we add it. So notice in all these problems, I'm combining all the different properties I know about exponents. And that is the key to what we're doing here.